Projective Geometry, Volume 1, by Owald, Veblen, and John Wesley Young. Chapter 6, Algebra of Points and One-Dimensional Coordinate Systems. Section 55, von Staudt's Algebra of Throws. We will now consider the number system of points on a line from a slightly different point of view. On page 60, we defined a throw as consisting of two ordered pairs of points on a line, and define two throws as equal when they are projective. The class of all throws which are projective, i.e. equal to a given throw, constitutes a class which we call a mark. Every throw determines one and only one mark, but each mark determines a whole class of throws. According to the fundamental theorem, Theorem 17 of Chapter 4, if three elements A, B, C of a throw and their places in the symbol T of AB, CD are given, the throw is completely determined by the mark to which it belongs. A given mark can be denoted by the symbol of any one of the projective throws which define it. We shall also denote marks by the small letters of the alphabet, and so, since the sign equal indicates the two symbols between which it stands denote the same thing, we may write T of AB, CD equal to A equal to B if A, B, T of AB, CD are notations for the same mark. Thus, T of AB, CD is equal to T of BA, DC is equal to T of CD, AB is equal to T of DC, BA are all symbols denoting the same mark by Theorem 2 of Chapter 3. According to the original definition of a throw, the four elements which compose it must be distinct. The term is now to be extended to include the following sets of two ordered pairs where A, B, C are distinct. The set of all throws of the type T of AB, CA is called a mark and denoted by infinity. The set of all throws of the type T of AB, CB is called a mark and is denoted by 0. The set of all throws of the type T of AB, CC is called a mark and is denoted by 1. It is readily seen that if P0, P1, P infinity are any 3 points of a line, there exists for every point P of the line a unique throw T of P infinity, P0, P1, P of the line. And conversely, for every mark, there is a unique point P. The mark infinity, by what precedes, corresponds to the point P infinity, the mark 0 to P0, and the mark 1 to P1. Definition: let T of AB, CD sub 1 be a throw of the mark A, and let T of AB, CD sub 2 be a throw of the mark B. Then, if D3 is determined by the quadrangular set Q of A D1B, A D2D3, the mark C of the throw T of AB, C D sub 3 is called the sum of the marks A and B and is denoted by A plus B. In symbols, A plus B is equal to C. Also the point D3' determined by Q of A D1C, B D2 D3' determines a mark with the symbol T of AB, C D3' equal to C', say, which is called the product of the marks A and B. In symbols, AB is equal to C'. As to the marks 0 and 1, to which these two definitions do not apply, we define further A plus 0 is equal to 0 plus A is equal to A. A times 0 is equal to 0 times A is equal to 0. And A times 1 is equal to 1 times A is equal to A. Since any 3 distinct points, A, B, C, may be projected into a fixed triple, P infinity, P1, P0, it follows that the operation of adding or multiplying marks may be performed on their representative throws of the form T of P infinity, P0, P1, P. By reference to Theorems 1 and 3, it is then clear that the class of all marks on a line, except infinity, forms a number system with respect to the operations of addition and multiplication just defined, which is isomorphic with the number system of points previously developed. This is, in brief, the method used by von Staudt to introduce analytic methods into geometry on a purely geometric basis. Footnote, chiefly referenced on page 141. Von Staudt used the notion of an involution on a line in defining addition and multiplication. The definition in terms of quadrangular sets is, however, essentially the same as his, by virtue of Theorem 27, Chapter 4. We have given it here partly on account of its historical importance, partly because it gives a concrete example of a number system isomorphic with the points of a line, and partly because it gives a natural introduction to the fundamental concept of the cross ratio of 4 points. This we proceed to derive in the next section. Footnote, chiefly section 53. Here, with every point on a line in which a scale has been established, is associated a mark which is the coordinate of the point. Projective Geometry, Volume 1. This book was written by Owald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renhold, with programming and illustration by Jim Renhold, 2019. Thank you for listening.